Hello everyone, welcome to ExamRat. My name is Shatabdi. I'm a second year medical student. Today we're going to be discussing about reflection of light. Last class we talked about image formation through concave mirrors, and I think that since it was a little different topic from what we have been studying for the past few lectures, we should go over it again. So let's just have a quick recap. So we talked about the laws of reflection, how angle of incidence will always be angle of equal to angle of reflection, provided that all 3 points are at the same plane. We talked about image formation by a plane mirror. It was a very easy concept, how distance between the object and the mirror will always be equal to the distance between the mirror and the image. Simple. And we talked about lateral inversion also and its applications. We talked about spherical mirrors. We understood certain terms that came with it, which helped us when we drew the pictures of the images formed by the spherical mirrors, right? So let's just go over this quickly. When the position of the object is at infinity, we know that all the parallel rays will come and will intersect at the focus, right? So the image will be diminished to a point. It will be real and inverted, but since it's a point, you can't see it, but you still have to write real, inverted, and highly diminished. Okay, when the object is placed beyond C, beyond the center of curvature, I hope you know by now what center of curvature means. So, when the object is placed beyond C, where will the image come? The image will come between focus and the center of curvature, and it will be real, inverted, and diminished. Okay. At C, we know where the image will be formed. It will also be formed exactly at the same point at C. What will be the characteristics of the image? It will be real, inverted, and of the same size. Okay. Now, as and when we are coming closer and closer with the object towards the pole, we know that the size of the image is increasing, right? So the next time when we put the object between F and C, obviously the image will be formed beyond C. This is the center of curvature. It will be formed beyond C, it will be real, inverted, and now it will be enlarged. When the object is placed at infinity, you know what will happen. All the rays after reflection will go towards infinity. So the image will be real, inverted, and highly enlarged. Okay. When the object is kept between F and P, we will no more get a real image. Now we will get a virtual image. So it will be virtual, enlarged, and an erect image. Okay, so that was it for concave mirror. Now, our topic of discussion today will be image formation by convex mirrors. Okay. So, if you can see at the picture here, you'll see that no matter where we are keeping the object, the image is always being formed between the pole and the focus. So this gives us an idea that in convex mirrors, it does not matter where the object is kept. Wherever it is kept, the image will always be formed between the focus and the pole. The image will always be virtual, erect, and diminished. So these three characteristics will always be there, and also image will be formed between pole and focus. Okay. So when we look at this one, what is it showing? That we are keeping the object. This is the convex mirror. We are keeping this is the pole. Okay, so now for a convex mirror, the focus will be here, right? So we can draw C here only and F here. This is the pole. Okay, so we are keeping the object, let's say, anywhere. We don't have to specify the position. So what's gonna happen? One parallel ray, one second, draw a little bit clearly. Yeah, so one parallel ray, after reflection, it will be, okay, so see now since I've drawn it like this, so you can accordingly like position your focus. Okay, so I could not bring it to the focus, so I'll just change the focus. But when you guys are drawing, please just draw it accurately to scale. Since I don't have a ruler, I have to just draw it normally. So what I can do is I can do a little bit of back calculation, and I can put the focus here, and I can put the center of curvature here. So yeah, but it's advised that you guys don't do back calculation. You guys just like measure the distance between the P and F and C. It will always be equal, so your ray diagrams will also be accurate. Don't forget to put the arrows. Okay, so this was one. Then the next ray we are going to pass it through the center of curvature. It did not happen, but yeah, just imagine that it passed through the center of curvature. So what's happening here is this ray is getting, you know that anything that passes through center of curvature follows the same path back, right? And since it's a virtual image, this will be dotted lines. So exactly the images are not, exactly the rays are not meeting. We are just making them appear to meet. That is the difference between a virtual and an real image, as we had talked about. So this is the image. So if this is AB, this is A dash B dash, and you know the characteristics. It is virtual, it is erect, and it is diminished. Okay, so this is the diagram. You guys can note it down and draw it by yourselves. Okay, so now we've talked about the image formation. Now why did the concave mirrors, convex mirrors, why did they come into existence? Like what was the need for them? Obviously it was not like just physics where we have to study it, right? We have certain applications. That is why it was formed, right? So here we're going to talk about some uses of concave mirrors. Okay, so basically you cannot see a real image cannot be seen, right? You have to take it down on a paper, which is a cumbersome process. So we do not use those applications. Which property of concave mirrors is mostly used is the fact that when an object is kept between the pole and the focus, this is the object, these are the rays, we basically get an enlarged object, enlarged virtual image, sorry. And so basically it is magnifying the image, right? And this property we are going to be using. Okay, so what is it saying here? Concave mirrors are commonly used in torches, searchlights, and vehicle headlights to get powerful parallel beams of light. They are often used as shaving mirrors to see larger images of the face, like I told you. The dentists use concave mirrors to see large images of the teeth of the patient. So both in these 2 points we are using this magnifying property. When it comes to torches, searchlights, and vehicle headlights, we are using the other property, that is basically giving a light from the focus so that after reflection it will be parallel, right? We are using that property. So for searchlights, torches, vehicle headlights, we are using this property, putting the light source at the focus. And for shaving mirrors, for dentists who use concave mirrors, we are using this property, the magnifying property. Large concave mirrors are used to concentrate sunlight to produce heat in solar furnaces. I think by now you have understood which property is this one. It is basically light coming from infinity will, where will all of them converge? They will converge at focus, right? So imagine if you keep a solar furnace here and all the sunbeams are coming and getting converged here, then we'll be able to produce a huge amount of solar energy, and then we can convert it into electrical energy and use it. So that is the main principle of solar energy, of the solar panels that are kept on top of houses. It is this logic only. So we talked about how the three different properties, the three different characteristics of concave mirrors have found its application in our day-to-day lives. One is focusing the beam from the focus so that parallel rays can be produced for long distances. We have learned about how if you keep of how when parallel rays are focused at one point, we get a huge amount of light at that particular point, and also the magnification point. Okay. Use of convex mirrors. We saw that convex mirrors only have one application, and that is to basically produce a diminished virtual erect image, right? Okay. So what is written here is that they are commonly used as rear view or wing mirrors in vehicles. So what are rear view mirrors? Basically, if this is a car, then you have seen that on both its sides there are two mirrors, right? Like if I'm drawing the front side of the car, like this is the front side of the car, then you've seen one mirror come out like this and one mirror come out like this, right? So these are basically rear view mirrors. Now what is their job? So while you are driving, lots of cars pass you by, right? From your left, from your right. So what happens is that if the driver is sitting here, okay. So what's basically happening is that the driver can see from this mirror the cars that are coming from way behind. Now how is that possible? That is possible by putting convex mirrors here. So what do? Basically they diminish the pictures, right? So even if the cars are huge, they will reduce it to a size where the driver can easily see all the big cars coming in this small area. Okay. So the mirrors are fitted on the sides of the vehicle, enabling the driver to see traffic behind him or her to facilitate safe driving. Why are they preferred? Because they are always given erect, although diminished image. Okay. Also, they have a wider field of view as they are curved outwards. Obviously, they are curved outwards, so they have a wider field of view. Thus, convex mirrors enable the driver to view much larger area than would be possible with a plane mirror. So they can see if this is the concave mirror, then you can understand that the concave mirror can basically converge light coming from this many area, which is like a huge area that it is covering, as opposed to a plane mirror. So if there was a plane mirror, it would just have been covering this much area, right? So that's about it. So that's why convex mirrors are used. Again, not only because diminished images they form, but because they have a larger field view. Okay. So now we come to sign convention. Now we've talked about objects, images, the position and all. Now what are we going to do is we are going to find out how the exact position of an image is being calculated. Till now we were like that, yeah, if it is put beyond center of curvature, then we'll get the image between the center of curvature and the focus. But how far from the mirror is it? What is the exact distance? That is what we are going to find out after knowing the sign convention. So first, let us know what it says. If this is, for example, a concave mirror, this is the pole, focus, center of curvature. Okay, so what is it saying? The object is always placed on the left of the mirror. Obviously, see, this is left, this is right. No confusion with that. So, always placed left of the mirror. Okay. Yes. This implies that light from the object falls on the mirror from the left side. Obviously, light is going from the left towards the right. All distances parallel to the principal axis are measured from the pole of the mirror. So whatever distance we take, like distance of the object from the pole, we will take with respect to the pole. All distances measured to the right of the origin are taken as positive, while those measured to the left of the origin are taken as negative. So what basically they are trying to say is that all the distances that we calculate from the pole towards the right, it is positive. So if this is the image here, then the distance will be, let's say, plus 4 meter, but the distance of the object from the pole or the object from the mirror will be minus 6 meter. So if it is in this direction, since we are calculating all the distances with respect to the pole, so when we are giving the direction, we are measuring something like distance of the image from the pole, it will be positive because this direction or from left to right is taken as the positive direction. So all the distances measured on to the right of the origin, that is along the plus x-axis, where according to the Cartesian system, this is the positive x, this is the negative x, positive y, negative y, right? So basically they are keeping pole at the middle. So everything with respect to the pole is being calculated. So with respect to the pole, if we go towards the right, it is obviously positive, and if we go here, it is negative. Okay. Distances measured perpendicular to and above the principal axis are taken positive. Very simple. So this is, for example, plus 4 centimeter. But if an object would have been kept like this, then it would have been minus 5 centimeter. So below the principal axis negative, above the principal axis positive. It's very simple. If you guys want, you can note it down after pausing the video. Okay. So we talked about the sign convention. So now it will be easier for us to understand the mirror formula. So the derivation of the mirror formula is not required. Just know certain terms. And that is, if this is the pole, this is F, this is C. If the object is kept here, then we know how we have to calculate the distance, right? We have to calculate the distance from the pole. So there's no need to draw the ray diagram here though. So what we are going to do is, this is, if this is O, then PO is equals to, is basically given by the letter U. Okay, so in this case it will always be minus. Let the image be formed here. The image can be formed here also, it's not a problem. So wherever it is formed, it will be see, if it is formed to the left of the pole, this is left, this is right. If it is formed towards the left of the pole, then it will be basically, it is V. So if it is formed towards the left of the pole, it is minus V. If it is formed towards the right of the pole, then it is plus V. In this case, let us take it on the left side only, because most concave mirror images are formed on the left side. So here, this distance approximately is V. So Pi equals to minus V. Okay. Now focus here. So we know that there is something called focal length also, right? So this we are again calculating from the pole, so it will be minus F. So now after the derivation, what comes as the mirror formula is that 1 by U plus 1 by V equals to 1 by F. This is basically your mirror formula. Now, while assigning the distance between the object and the pole and the image and the pole, I had given the negative signs. But while you are writing the formula, when you write the formula, you don't have to give any sign conventions. You don't have to write minus U, minus V, minus F here. It is not required. But what you have to do is, when you are giving the magnitudes, like for example, if I say U in this case, in this image, let U be minus 25 centimeter, then while you are calculating, you have to give minus 25 here. Okay, you cannot just negate the minus sign. While writing the formula, you don't have to give the minus, but when you are writing the actual magnitude, then you have to give the sign, because that is how you will be getting the accurate value. Okay, so we got the mirror formula here, where U is the distance, is the object distance, you can say, V is the image distance, you can say, and F is obviously the focal length. Okay. Now magnification. What is magnification? By the term, from when we were kids, we have known about magnification, about what is, like, how we can see a small thing magnify into a big object, big image rather, when we have used a magnifying glass. Okay, so basically, after talking about concave mirror, convex mirrors, you've understood that magnification is both ways, right? So either the image is bigger than the object, or the object is bigger than the image, right? So in that case, if we compare the object and the image size, so for example, if size of the object is greater than size of the image, then magnification will be calculated as, magnification's formula is always how much the image is larger or smaller than the object, right? Like that is how magnification is calculated. Now, whether this fraction will be greater than 1 or less than 1 will depend on what is the size of the object. So in this case, I have told you that the size of the object is greater than the size of the image. So you'll obviously understand that here the magnification will always be less than 1, because the denominator is bigger. So it is less than 1 in this case. So now this is the particular case I told you about. Okay. When we talk about the exact formula that had come after derivation, it is basically, one way of writing it is m equals to height of the image by height of the object, or it can be also written as minus v by u, where you know so where you know that v equals to image distance, u is equals to object distance, right? So for now, the derivation is not important. You just have to remember the formula that m can also be written as minus v by u. So this is going to help us when we're going to solve sums. So even if sometimes you don't get the height of the image and the object, they will give you the distance between the object and the pole and the image and the pole, and they will tell you find the magnification. So don't forget this formula. This is also very important. So by this we come to the end of the discussion of the reflection of light and the image formed by convex mirror, concave mirrors, their uses. In the next class we are going to start with refraction. And in reflection, we are going to be also dealing with images formed by lenses this time. So, thank you for watching.